Hello dear students, dear friends, dear guys. In this video we are going to work out Schrodinger's time dependent wave equation. So in the previous video we have worked out Schrodinger's time independent wave equation, and we started with the wave function psi as a e to the power of I kx minus omega t, and this k is a propagation vector and its value is 2 pi by lambda, and this omega is angular frequency and can be written as 2 pi nu. Now if here I multiply this with h bar, I will multiply this also with h bar. So in this case you have seen this h bar k is nothing but the momentum, and this h bar omega is energy. So these values we have to keep in mind. H cross k is P and h bar omega is E. Now let us take a partial derivative of this wave function. In fact, the double derivative of this wave function psi with respect to x. So this is del psi upon del x. This will be iota k psi. And if you take its another derivative, del 2 psi del x2, this will come out to be minus k square psi. So we will keep this equation in mind. May number it, may call it 1 for the time being. So now let's take the time derivative of this wave function. The time derivative of this wave function will be del psi upon del t. Now that will be minus I omega psi. Okay, this omega is, we have seen that this E is h bar omega. This implies this omega can be written as E by h bar. So in doing so, we can substitute the value of omega in this equation. And doing so, here instead of omega, we are going to write E by h bar. So we can have a shift. This h bar can be brought here. So I will just rub it over here. And this iota will be transferred here. And it will become iota. It will go to the denominator, then you will multiply with iota, and in the denominator you will have iota square, that's equal to minus 1, and finally you will get I h bar del psi by del t is equal to E psi. Alright, now freaking out this E, if I write down this E as the summation of kinetic energy, that's 1/2 of mv square, and potential energy along x, subjecting the system to some external force, I can write down this E as P square by 2m plus V of x. So this E is the total energy. This E must be equal to P square by 2m plus V of x, subjecting the system to some external force. So in this case, if we proceed looking for this P was already evaluated in terms of h bar. What was that? That was h bar K is equal to P. That means h bar square K square must be equal to P square. So we can use P square here. Instead of P square, I will use h bar square K square. Now, the equation that I noted down as equation 1, in that equation, we could write down K square. Now, what is this K square? So this E can be written as, this is h bar square divided by 2m. And instead of K square, better is to use this E in this equation first. If I use this in this equation, what I'll get here is, this is here E, okay? E is h bar square K square by 2m plus V of x psi. So this is del psi upon del t. Okay, if you rightly go back to that equation containing K square, so here if I write this equation like this, I h bar del psi upon del t must be equal to h bar square K square by 2m psi plus V of x psi. Now, this K square psi can be written down from the equation 1 that I had noted down. Now, what was that? So here I will write I h bar del psi upon del t. So will be equal to this h bar square by 2m. That will be minus del 2 psi upon del x2. And here I'll write plus V of x psi. So I can say that the equation that's here, that we have achieved here, this is the Schrodinger's time-dependent wave equation. So this is I h bar del psi upon del t is equal to minus h bar square by 2m del 2 psi upon del x2 plus V of x psi. Now, if we incorporate all the three dimensions, x, y, and z, and you rightly remember that the del 2 by del x2 plus del 2 by del y2 plus del 2 by del z2 is equal to the Laplacian operator. So I can write this time-dependent Schrodinger wave equation in three dimensions as I h bar del psi upon del t is equal to minus h bar square by 2m del square psi plus V of x psi. So this is the equation. This is the time-dependent Schrodinger's wave equation. And this equation is considered to be the basic mathematical formulation of Hello dear students All right, in this video, I'll be talking about the validity of Schrodinger's wave equations. And it would be right to say that we have used a wild leap in reaching out to the result of writing down Schrodinger's time-dependent equation as well as Schrodinger's time-independent wave equation. Now the point is that that the actual problems that are out there, the actual problems have a different set of constraints involved in them. So there can be any other approaches by virtue of which one can lead to the formal representation of Schrodinger's wave equation. In addition of this, the Schrodinger's wave equation should be inculcated with some legal postulates. Now, what I say the legal postulate, if we incorporate a postulate in Schrodinger's equation and work out this postulate for some particular problem of concern and achieve certain results out of it, the moment we compare the results that are predicted by solving the Schrodinger's wave equation, if these results are if these results are in close agreement with the experiment that has been performed on the same problem, then the postulate can be taken out, correct for that particular problem. But if at the same time a postulate has been incorporated and certain results are achieved out of it, and on comparing these results with the experiments performed on the same problem that has been considered, then in that case, the postulate that has been incorporated in Schrodinger's wave equation should be removed. In general principle, we should say that Schrodinger's wave equation in itself is a principle. You don't need any other means, and there cannot be any other means by virtue of which you can reach out to a result of Schrodinger's wave equation, because Schrodinger's wave equation is in itself a principle. As if we see into the domain of classical mechanics, the Newton's second law of motion, that's a very fundamental equation that works in most of the classical problems of classical physics. So you cannot achieve a result of Newton's second law of motion by virtue of some other means. But the fact of matter here is that if you can achieve this Newton's second law of motion from Schrodinger's wave equation, provided the quantities that we are working out are the averages. If we take out the quantities as averages of their measurements, then we can certainly have a derivation of Newton's second law of motion from Schrodinger's wave equation. So, to be precise, the Newton's second law of motion, it's in itself a principle in the domain of classical mechanics. In the similar fashion, the Schrodinger's wave equation in quantum mechanics, in wave mechanics, is in itself a principle, and the point is that the postulates that we are using to solve the Schrodinger's wave equation, whether it is consistent with the experiments out there or not. Moreover, I would like to say you that this Schrodinger's wave equation is applicable in almost in all situations except relativistic situations. In relativistic situations, a more detailed formalism is out there in terms of wave mechanics.